So I now want to talk about dark energy, the fact that the expansion of the universe is speeding up, not slowing down. And it's a puzzle that my colleagues accuse me of wandering around the halls of the University of Chicago saying dark matter is the most profound problem in all of science. And I'll end with that. So you know the universe is expanding. And Edwin Hubble found the evidence for the expansion. And that galaxy in the middle is ours. And what he found in the 1920s is other galaxies are moving away from us. And the ones that are farther are moving faster. So Einstein interpreted this in an amazing way, which is the galaxies aren't moving. What's really happening is space is expanding, and the galaxies are being carried along. And space is expanding uniformly, and that's why the galaxies that are farther away look to be moving faster, because when you expand space uniformly, the galaxies that are farther away are being carried greater distances as the universe expands. Okay, so you all know that. And let me just do, this is the Harvard part of the talk. You know, are we at the center of the universe? You know, well, at Harvard, everyone's at the center of their universe. And so here's a universe. These are galaxies. And then through the miracle of PowerPoint, I can expand it. Does that look a little bigger? And then I can expand it again, and that looks a little bigger. And so we'll now address this question of, are we at the center of the universe? We should take a vote. That's how we do things in science. Now, how many people think we're at the center of the universe? How many think we're not? Okay, pretty evenly split. I guess we don't know the answer to that one. So now let's look at what this looks like from the perspective of different galaxies. So let's pick that one, and then superimpose those three pictures. 1, 2, 3. I've superimposed the three pictures. And remember, those three pictures are like 3 different times. And so what you can see is, from the perspective of that galaxy there, it sees the other galaxies moving away from it. And if you look at the spatial relations here, the ones that are farther away are moving faster. Right? In the time between the 3 frames, they've gone farther. And so from the perspective of that galaxy, it's a Harvard student. It's at the center of the universe. If we look at the perspective from another galaxy, say that one, and just take those, the 3 different images and now line them up on that galaxy, bop, bop. After you get adjusted to it, remarkably, you see the same picture. It sees all the other galaxies moving away from it, and the ones that are further away look like they're covering more distance, are moving faster. And, I last gave this talk in LA, so, in LA you have to do this a 3rd time. So there you go. Okay, but you guys are New Yorkers, you're smart, you don't. So this Einstein's interpretation of this, that space is expanding uniformly in all directions, explains Hubble's data and says that everyone's at the center of the universe. Now, the one tricky thing here, before somebody tries to nail me with this, is that, of course, if you're near the edge here, you're going to ask, what about the edge? Well, I forgot to tell you that I only showed you part of the universe, right? It goes on forever. And so because of this, so no center, different perspectives, because of this, we can describe the evolution of the universe. It's just a scaling up. It just scales up with time. And so this is how a cosmologist thinks about the evolution of the universe, is that the size increases with time. So those are those green curves, and time is this axis, and size is that axis. And it started out really small. That's what we call the Big Bang. And its size is increasing with time. And notice that, and I'm going to use a technical term. I apologize for using a technical term here, that the lines are droopy. So notice that the rate at which the universe is getting bigger is slowing. The lines are drooping. That's because gravity should be slowing the expansion, right? And so the big question up until about 20 years ago was, is there enough stuff in the universe to cause the universe to slow down, halt, so that's the bottom curve, and then fall back on itself? So a universe with lots of stuff, gravity would halt the expansion, it would recollapse. The upper curve is a universe with less stuff, and gravity would not do that. It would eventually, notice it goes to kind of a straight line there, it stops slowing down, and then there's Goldilocks in the middle. You know, slowing and slowing and slowing, and an infinite time after the Big Bang stops. And then there's a relationship between the amount of stuff in the universe and the shape of the universe. So a high-density universe, the bottom one, curves back on itself, and a low-density universe is curved like a potato chip, and Goldilocks is not curved at all. And so this is a slide, probably it wasn't a slide, but I know you all learned this on your mother's knee. There are three kinds of universes, right? And once we figure out the slowing of the universe, we will have figured out the destiny of the universe. This is what your mother told you. And so this has been a hot question in cosmology for a very long time. And how would you go about measuring the slowing? Alan talked about measuring the shape. So a puzzle to think about here will be, let's see, we're the uncurved universe. So how does that work in these pictures? We'll come back to that at the very end. So I'm going to come back to this idea that the telescope is a time machine. And that's how we can measure the slowing. So this literally looks like Hubble's famous diagram, where he plotted velocity, apparent velocity of the galaxy against its distance. And what Hubble found was this straight line relationship between the two, that the galaxies that are further away are moving faster. And if we remember what Einstein told us, if we measured galaxy distances and apparent velocities today, I'm going to tell you in a second we can't do that, but if we did, we would get absolutely a straight line because the expansion of the universe is just a stretching of space. And so that's that straight line that's dotted. But we can't measure the velocities today because the telescope is a time machine. And when we look back at very distant galaxies, we're measuring their speeds way back when. So now this is going to be the hardest 30 seconds in the talk, so I want you to concentrate. So if we could measure the velocities today, we would get a straight line. Let's suppose the universe is slowing down. And now let's remember that we're actually measuring the velocities way back when. So if that broken line are the velocities today and the universe is slowing down, then way back when the data points should fall above the straight line. They were moving faster. And so what cosmologists have been trying to do for a very long time is look at the deviation of, they call it Hubble's law, from a straight line, and measure that slight upward curvature. The reason it's hard to do is not just because they're not as smart as theorists, although that's part of it. Nah, don't tell them I said that. What's hard to do is getting the distances. It's hard to measure the distance to a galaxy. The velocities, I don't want to go into it, but we measure velocities the same way that a policeman uses. Of course, no one in New York drives a car, but you've heard of cars, right? And you know that there are radar guns, and you know they use the Doppler shift to measure the velocity. That's how we do galaxies. The distances, we basically need a standard candle. So the technique we use is called a standard candle. And you all know about standard candles. Oh, but you don't drive cars. But you know, if you take a light bulb and you move it away from you, it gets fainter. And so if you had if every galaxy in the universe carried a light bulb, a standard light bulb, and then we were able to look at that standard light bulb, the faintness of that standard light bulb would just tell you how far away that galaxy is. So that's the theorists, you know. Okay, so that's what a standard candle is. But of course, the universe is big and it's hard to see distant galaxies. So how do we actually do it? Well, that's been a problem over the years, is standard candles is there aren't really good standard candles. A number of years ago, astronomers discovered a pretty good standard candle, and it's called a Type 1a supernova. Let me tell you what a Type 1a supernova is. It's a star that's about 40% bigger than our sun that undergoes a thermonuclear explosion and obliterates itself. And so it's a 1.4 solar mass thermonuclear bomb. So without going into the details, that sounds pretty standard if it's a fixed size. And the nice thing about it is you can see them across the universe. So there's, up in the corner, there's a very distant galaxy. There's a Type 1a supernova. It's as bright as the galaxy. And each one of those is the same. So they're easy to see. There's only one catch. And the catch is that these supernovae don't go off very often, about once in 100 years per galaxy. But I know you're all paying attention. The expansion of the universe is the same in all directions. So it doesn't matter which galaxy's distance you measure. They all fall on that Hubble line. And so you just have to study enough galaxies. And, I was going to tell you what my colleagues at the University of Chicago do numerical isn't that beautiful? So it's actually a white dwarf star that's accreting material from a smaller star, and it eventually pushes it over and causes it to explode. And we think we even understand why they're standard candles. So how do we do this? A key technological breakthrough, here's my other technology bit, are big electronic cameras, because you don't want to wait 100 years and stare at one galaxy. But if you stare at 100,000 galaxies, for example, then 1,000 of them will have a supernova in a year. So that's math I can do. And so, but how do you stare at a large number of galaxies? Well, you have a really big camera. And so that was the technological breakthrough, the same technological breakthrough that you have in your iPhone. Or, well, not all of you have iPhones, but... and so let me show you how it works. You take a picture of a big chunk of the sky where there's, let's say, 10,000 galaxies on, let's pick a date, May 15th. And then you come back on May 30th and you take a picture of that same sky, and then you subtract the two pictures and see if anything went bump in the night. And that's what was done here. So the background is a picture from a ground-based telescope of lots of galaxies. And see that little square that's blown up? So it's blown up so that you can see an image of two galaxies next to one another. One is the before, and the other one is the after. And you'll notice that the galaxy in the upper left corner looks different. And when you subtract those two images, do you see the one that says difference? This one right here says difference. You see right there that something was different. There was a supernova in that galaxy. And now you task the Hubble Space Telescope to go look at it, and that upper image is an image from the Hubble Space Telescope. Okay, and what do you find? Now we're back to cartoons. So those little blue things are the data, and oops, I must have screwed this up, right? Because the data are not above the straight line. That would be a slowing universe. The data are below the straight line. And so, in fact, after 80-some years of trying to measure the slowdown of the universe, it's actually speeding up. And so that was extraordinary. There were two teams involved, one led by Adam Rees and Brian Schmidt, and the other led by Saul Perlmutter. Very competitive team. Science is a great human activity, and there's competition, and I can tell a little story about them. You would have thunk that the biggest surprise that they would have had when they made this discovery was that the universe was speeding up and not slowing down. That was not the biggest surprise. The biggest surprise to each of the teams was that they got the same answer as the other team, because both teams thought the other teams were fools. And this team was the physicists team, and these were the astronomers, and the astronomers thought, you know, these guys don't even know what a magnitude is, let alone a supernova. And so big discovery, cover of Science magazine in 1998, and there's Carl Sagan reminding us that extraordinary results, or no, what does it say? Extraordinary claims require extraordinary evidence. So that was in 1998, and long story short, we now have the extraordinary evidence. The two teams collected about 50 supernovae each. Since then, we've added another couple of thousand, plus different lines of evidence. And in fact, this again is the microwave background, these curves. And if you remember Alan Guth's omega parameter, the total amount of stuff is the critical density. Matter is only about 30% of that. This whole story only works if there's something else out there, like dark energy. So this is an indirect method, but we now have the extraordinary evidence. So if Carl Sagan were still around, I think he would, you know, I don't know if he would do 2 thumbs up or 1 thumb up. The universe really is speeding up. Now actually, oh, and most importantly, this was certified by Sweden. So in 2011, Stockholm certified this by giving the Nobel Prize to Adam, Brian, and Saul for this remarkable discovery. And if you come back to this morning, to the boring part of today, sorry, the little choke collar just went off there. They gave Andre the controls on it now. This discovery was really important to those of us who, in their other life, study inflation, because inflation went out way on a limb saying that the universe has the critical density. And Alan Guth told you this morning that, you know, towards the end of the 90s, it was looking like we were coming up a factor of 3 short. And all of a sudden, this rescued inflation. So this was a really big deal. But we have a higher standard. Theorists have a higher standard. Sir Arthur Eddington, one of the great astrophysicists of the 20th century, put it this way: no experimental results should be accepted until confirmed by theory. And, oh, this is a smart group. If you have a mixed group of theorists and experimentalists, you have a bimodal laugh. The theorists laughed immediately, they get it. And then there's kind of a tail a little bit later from the experimentalists. And of course, all I'm saying is that science is not just a notebook of facts. It's understanding about nature. And so that's all that says, that if we can't understand some of the facts that we gather, they may be too good to be true.